Now that we've talked about a handful of ways that we could represent digital circuits, from truth tables with Boolean expressions, circuit diagrams, and timing diagrams, let's now talk about how we can design even more complex circuits. So for this video, we'll talk a little bit about structural modeling. So as our circuits start to become more complex, we'd like some more manageable and easy ways to design these circuits. And so one way to do this is to break this down into smaller components and connect these in a structural fashion. So for example, my circuit, I'll break this down into submodules, which are then connected in a certain way. This is also known as a modular or hierarchical design. By making my design modular, or separating out each of the components, I have several benefits here. So one is that now I can individually test subcomponents, making it easier to design and test these, and then compose larger circuits. I can also reuse modules. If I have the same module, I can make copies of it and reuse the same module which I've already tested. So let's look at a specific example where this would work. So coming back to addition, let's say I had to add two 3-bit numbers. And I can remember how this is done. I look at the first one position, add the 2 bits, 1 plus 1 is 2, so I have a 0 as a sum, a carry to the next position. 1 plus 1 is 2, again a 0 and then a carry, and 1 plus 0 is 0, and then I get a carry. So now if I wanted to design a circuit that added two 3-bit numbers, I could do what we've done before and directly describe a truth table for this function, come up with an expression using SOP, and in fact I could use a K-map to minimize it. Or, because we've already created, let's say, a half adder and a full adder component, so the full adder takes 3 bits of input, two bits A and B to add, plus also a carry in, and then outputs a sum bit and also a carry out. So I can look at now composing a 3-bit adder in this case, using these full adders which we've already tested and built. Okay, so my 3-bit adder has two 3-bit inputs and a 4-bit output. And because I already have this full adder component, which I've created, I know it's working, I'm going to go ahead and reuse these modules to build this 3-bit adder. The first full adder will take the least significant bits of both A and B, so we'll call these A0 and B0. Second full adder will take the next two significant bits of A and B. And the third will take the most significant bits. Now the carry-ins, for the least significant bits, the carry-in, well, there's no carry-in, so this will just be 0. But the carry-out will become the carry-in for the second full adder, which adds the next two significant bits. And same thing for the carry-out for that full adder will go on to the next one. And then the sum will be the concatenation of all the sum bits, S0, S1, S2, and the final carry-out. So the concatenation of the carry-out, the final carry-out from the full adder, and the 3 sum bits makes up my sum for this 3-bit adder. So this is an example of a structural design where we have the individual components and we're wiring them up with internal signals and reusing modules, smaller modules, which we've already designed and tested. So now let's talk about how this would look like in Verilog, in a hardware description language. So Verilog is very good for doing these types of structural designs. So let's first say that I've already created my full adder design. So I have a module, full adder. It has 3 inputs. And 2 outputs. So inside this module, we could put the full adder logic. Now I could reuse this module inside my 3-bit adder, so I'll call this a 3-bit adder, or if I want, we can also, the other name for this circuit is it's called a ripple carry adder. So we'll call this RCA3. It has 2 3-bit inputs. So A is a vector with 3 bits. Same thing for B, and my output is a vector of 4 bits. So first thing I'm going to do is I'm going to instantiate 3 of these full adder modules inside my RCA. So I give it the name of the module, in this case FA, and then I'll give this specific component a name, a unique name. So I'll call this F1. And then in parentheses, I'm going to give the port list for this module and connect them to the internal signals. So in this case, I could just list in the order that they appear, for example, in the full adder, or in Verilog syntax, I can also list the port name specifically. So in this case, A, and then give the port. So for this one, it would be A, bit 0, B, bit 0, the carry we're going to use is tied to 0. So I'm going to go ahead and create an internal wire here for not only the first carry, but I'm going to create a vector for all these internal wires here for the carry signals. So this we'll call wire. And then I'll assign to the first carry in, do a continuous assignment statement. So I'm tying this continuously to 0. And then the carry in for this first full adder module will simply be carry 0. Okay, now we have 2 outputs from the full adder. So the output C out will be connected to my new wire internal to this ripple carry adder, this one right here, which we'll call carry 1. And then the sum will create a new wire for this one, and we'll call this sum for our output. And so this will be sum 0. Okay, so now we need to add 2 more, instantiate 2 more of these full adders. So I'm just going to go ahead and copy and paste this guy because it's going to look very similar right below here. So the second one, we'll just call this one F2. And the inputs for this guy, so it's going to take A1 and B1. The carry in now will be carry 1. It's the output carry out from the first full adder. And the carry out will be C carry 2. And then the sum will be sum 1. Okay, and then you can probably guess, go ahead and do the same thing for the third full adder. Call this one F3. This one takes as inputs A2 and B2. Carry 2 is the carry in, and carry 3 is the carry out. And actually in this case, I'm going to go ahead and connect carry 3 is the same thing as the most significant sum bit. So we're going to tie the carry out to sum and make sure our vector is the same here. It's 4 bits, so 3 down to 0 for the sum. And then the sum from the last full adder is going to be sum 2. And so now we have our ripple carry adder, which we've created with a structural model. Now, important thing to note here, each of these components we've instantiated, these full adders in this case, can happen in any order. All of these components, as well as the continuous signal assignments, such as this one, all happen in parallel. So the order can change in these, and I'm going to get the exact same design.